minimize that and bring that up. All right, so we are going to start, or we're going to start into our last unit here on organic chemistry. There is one other unit that we're not going to get to. It's on electrochemistry. I will have one lesson on it, just to talk about what it is and a little kind of introduction to it, but there will not be a test or quiz on it. There will be a question or two on the exam on that last lesson. There will be a test, and I think at this point it's something like set for the Thursday of next week, right? So it's a short kind of little unit. It's kind of condensed with a couple of labs in there, and then a test. The labs that we do are not, they're just fill-in-blank type labs, so they're pretty straightforward. Okay, organic chemistry. So you don't have to rewrite that. You can write the words down, though. That's all important stuff, and I hate the animations. So organic chemistry is the branch of chemistry that studies organic compounds. Now, we've got to be careful with the term organic when it comes to chemistry. And that's even more true today than it has been in the past because of the term organic being applied to food, right? Is it organic? In terms of food, the term organic implies that it's been grown in such a way that synthetic chemicals have not been used to promote the growth or to protect it from various, bugs, disease, fungus, et cetera, so herbicides and other types of sprays. Historically, the term organic used to mean to originate from plants and animals. So chemists realized soon after, starting to discover various types of compounds that there were many and many, many compounds that contained carbon. A vast number of compounds that contained carbon. And we still use that as one of the definitions. Carbon is the principal element. Carbon is covalently bonded to other elements such as other carbons, hydrogen, oxygen, nitrogen, etc. Now, early on in the world of chemistry, it was determined that these carbon compounds predominantly came from living things. Things like plants and animals. They actually believed that there was something special about a living thing that could endow the organic chemical with special properties, almost like some kind of magic. They even had a term for it. They used to call it the vital force, that a force of vitality was needed to create these chemicals, and that you couldn't make them in the laboratory. And then a chemist by the name of Friedrich Wöhler, I can't say it correctly, he was German, maybe like a V, Wöhler or something like that. It makes no difference. He took some what was believed to be inorganic chemicals, things like cyanide. These don't count as organic. We'll talk about why that is. He put it in a reaction vessel, heated it, cooked it up. I believe he even used an electric discharge, some electrodes, zapped it, did all kinds of stuff to it. And eventually he discovered these white crystals were being formed. And when he studied the white crystals, he found a chemical called urea. Now, urea is a chemical that's found in urine. And if you evaporate urine, you will get these white crystals, urea. It's often used as a fertilizer, this white crystal-line structure called urea. And again, it was believed that only living things could produce this type of chemical, but this gentleman did it in the laboratory. So that changed things greatly in that chemists realized that there wasn't anything special about the living thing to produce the organic chemicals. It was the way that the carbon was bonded to other elements. okay? So typically we need carbon bonded to carbon in some way. And if we look here, carbon monoxide is carbon bonded just to an oxygen, that's it. That's not an organic chemical. Carbon dioxide, carbon bonded to two oxygens. Still, there's no carbon, carbon, carbon. There's no carbons bonded to carbons. So it's also not an organic chemical. This is the bicarbonate ion, carbon bonded to oxygens and hydrogens, not an organic chemical. So you can't just look at the types of elements that are in it. You've got to see how it's bonded together in order to see whether it's organic or not. CN, cyanide, carbon bonded to a nitrogen, not organic, all right? And then all of the other chemicals we've talked about up to this point. Sodium chloride, definitely no carbons in there. That's not organic, all right? So all of our ionic compounds, they're not organic compounds. So we have to have these carbons bonded to other carbons in some way. Okay. You can write down the bullet that there are several million organic compounds, but don't write down the lists of naturally occurring versus synthetic. Don't worry about that. Again, many of them are naturally occurring. They come from living things. Glucose, sucrose, those are sugars. DNA is what, found in the nucleus of a cell, important for something? Life, maybe? I don't know. You'd have to ask a biologist. I don't really know biology very well. Oils, fats, cellulose, that's the stringy fibers in a tree, you know, cellulose fibers, paper, starch, and then synthetic ones. Plastics are made of carbons. Various medicines, that's not to say that all medicines are, but you know, synthetic drugs, not stuff that's coming from nature. There are medicines that come from nature. Gasoline, alcohols, etc., etc. All kinds of different organic compounds. Millions and millions of them. Okay? All right. Let me know if I'm going too fast. So why is it that carbon is so good at doing its things? You can write those three things down. What is it that makes carbon so special? Well, number one is the big one. Carbon sits right there in the middle of our step of 8 atoms across the top, which means it can share 4 electrons. That means it can make 4 bonds with something, and it can make single bonds or double bonds or triple bonds. It can bond in all kinds of different ways. Put carbon atoms together, you can get chains of them. You can get them to form rings. Here we've got a ring structure. They can form spheres. This one right here is a sphere made up of 60 carbon atoms bonded together. You can make flat sheets of carbon atoms. Here they are there. The flat sheets are sometimes called graphite. If you're using a pencil right now, a lead pencil, there's not lead in there, it's graphite made up of these sheets of carbon that when you write across the paper, you're laying down these little sheets of carbon. They make that kind of gray color. Here we've got a complex structure at the top there. That's a diamond. Diamond is made up of carbon. Would diamond count as an organic compound? I don't know. I should know that. I don't think it does. But it is made up of all carbon, yep. Carbon nanotubes, right here, that's a representation. If you were to take a sheet of the carbon, right, which is called graphite or sometimes graphene, chemists have a way to heat them unevenly and then they curl up a little bit because of the heat. And when they meet, they'll make a bond and they'll make a tube. That is a cylinder of carbons. That's a carbon nanotube. If you take the sphere and you work very carefully with the chemicals, you can put a sphere on the end of the tube and actually make like a capsule of carbon atoms. All right? Chemists thought at one point they would be perfect at maybe delivering drugs to cells. You could put like a single drug molecule inside the carbon nanotube and have it go right into the cell and drop off the drug. That's what they were thinking maybe 5, 6 years ago. They were saying, this is going to be awesome. Then they did studies on nanotubes, and nanotubes on living matter don't do good things. They cause cancer. The cells tend to react negatively to the carbon nanotubes. So they're still thinking of ways in which they can use them. These are all very new things, these nanotubes and graphene and these balls. The nanotubes, maybe 8 years in terms of research being done. So that's really cutting edge on chemistry. Yeah. They can form combinations of single, double, and triple bonds with each other. All right, so they can bond in many different ways. Really, they're like, it's like Lego. You can put Lego together in many different ways. Carbon is able to do that. If you have something like a fluorine, it can only have one bond. It can only stick to things in one way. So it's not able to do so many things. Okay, that's just some more pictures of the double bonds. Am I good to go? So hydrocarbons, let's define what hydrocarbons are, and then we will talk a little bit about where they come from. So we're going to start, and the majority of this unit, we're going to spend talking about the simplest type of organic chemicals. We're not going to include any O's or N's like we said in that one slide. We're going to start with just C's and H's, the simplest types of organic chemicals. And we can put these simple organic chemicals into one of 3 groups. And they're called alkanes, alkenes, and alkynes. Today we're going to learn about alkanes and how to name them and how to draw them. Tomorrow we're going to do a lab on where these chemicals come from. I'm going to distill some oil because oil is a predominant source of organic chemicals. And then on Wednesday we'll talk about the alkenes and the alkynes. Again, I'm not sure where everyone is at. Everybody's writing at different places. Okay, so let's talk a little bit about what alkanes are before we do the video, and you can see there, Intro to Carbon Chemistry video. That's where I'm going to click on that. And then we'll go to that sheet. So alkanes are the simplest because they only contain single bonds. Alkanes are special because they have a property called saturated. They're saturated hydrocarbons. And after the video, I will talk more about what I mean by saturated. And you've heard of saturated before. You may have heard the term saturated to describe something that's like soaked with water, but that's really not what we're talking about. If you've talked about maybe in a health or a foods class about saturated fats versus unsaturated fats, this is what we're talking about. I'll explain how it relates over once we get through the video. So there you can see there a little link to some food facts there. Animal fats such as butter, milk, bacon, they are considered, or they are saturated fats. We'll talk about what that means. It means that they've got the maximum number of hydrogens, but I'll go into more detail on that. So once you're done that slide, you can open up that document on the carbon chemistry video, and you can either type your answers in right into your document, or you can write it out. I don't care. Now, at the beginning of that sheet, it asks you to define what organic chemistry is and what hydrocarbons are, but we're going to forget about that because we've just done that in our note. I actually should have deleted that away. That's something I did years ago, but now we've already got that written down in the note. There's no need to rewrite it. Now this video at the very beginning, and it's really the beginning that we're interested in, is going to talk about a process that is used to separate crude oil into the various types of hydrocarbons. So this is a little introduction on how we obtain the majority of our organic chemicals from crude oil out of the ground, and how we can separate that crude oil into the individual types of hydrocarbons that we can encounter. And again, like I said, tomorrow we're going to work in the lab, and I'm gonna take some crude oil and we're going to distill it. We're going to separate it into the different hydrocarbons, and then we will do some tests on viscosity, how thick it is, how viscous it is, and also flammability. So we'll see how flammable various hydrocarbons are. All right. Are we good here at this point? Now this is where I'm not sure whether it's going to work or not. I am making a video and it's recording. At least I hope it's recording. Maybe it isn't even recording. Am I still recording? Yeah, it's recording. And I'm going to try to record the video. The audio isn't going to be good, but at least whoever's watching will be able to see kind of what we're doing. So this is on YouTube here, and hopefully we can play it and get some sound. I may have to stop the video though, because I know the sound output didn't work in the past with it running. So let's take a look. Oh, we do have sound. Awesome. Okay, so let's pause here for a moment. So like I said, the very beginning of that sheet talks about, or has you define organic chemistry and has you define hydrocarbons. Well, you just did that in your notes, so let's not bother with that. I won't pause it when we get to those. But for the rest of the questions that are being answered, I will pause and we'll have a chance for discussion and a chance for you to write things down, okay? So let's go full screen here and let's get things running.
The living world around us is made up of carbon compounds. Life is based firmly on this remarkable element. The useful property of carbon is an electron arrangement, allowing 4 bonds to form with other atoms. It can also bond with itself. These simple properties can lead to half the known compounds being compounds centered around carbon. The study of carbon compounds and their properties is called organic chemistry. Carbon compounds easily fall into families or series. The first class of organic compounds are the hydrocarbons, containing the elements hydrogen and carbon. This is divided into aliphatic and aromatic hydrocarbons. Carbons contain which have hydrogen.
We won't be talking about benzene structures in this unit.
Are usually chain compounds that do not contain the benzene ring. They're single bonds, amines with double bonds, and alkynes with triple bonds. To understand the naming of in which all the carbon atoms are singly bonded to one another. Methane is a single carbon atom combined with 4 hydrogen atoms. Ethane has an extra carbon with the unused bond occupied by hydrogen. Propane has 3. Butane has 4 carbons. Pentane 5. 6. Heptane 7. Octane 8. Nonane 9. And decane. After that, we usually just give the number. For example, C25. So this table shows us the basis of naming hydrocarbons.
Okay, and I'll pause that there for a moment because that then can give you an opportunity to fill in your chart. So number of carbons, if there's one carbon, we use a prefix at the beginning of the word, and that is meth. If there's two carbons, it's eth. 3 carbons is prop. 4 carbons is, it says but we would pronounce it bute because it usually comes with an ane after it. So butane, so bute. And those are pretty tricky because they don't really, we don't have anything to kind of link to any previous knowledge for that 1 to 4, meth, eth, prop, bute. Prop comes from propane, but you probably didn't realize that there were 3 carbons in it. Now after 4, you get pent, like a pentagon, and hex, like a hexagon, and hept. I don't think it's called a heptagon, is it? Is that what it's called? Is it a heptagon? Awesome, then that works out perfectly. Oct for 8, non for 9, and 10 for dex. So those make sense, I think. For it's the first 4 that you've got to really kind of learn, I guess, because the rest of them come from previous knowledge from geometry. And again, I have no idea what we're doing, whether we're writing it down or putting it in the document. Just let me know when we're good to go. We're good to go? Good to go? Good to go? All right.
The carbon atoms don't need to string together in a long chain, as in our molecules so far. For example, we can have C4H. However, in methylpropane, we see the formula is still C4H0.
Of the lesson, chemical formula